This lesson is entitled Continuity versus Differentiability. Rather than define continuity here, we'll just tell you a function is not continuous at a point if there's a break at the point. Okay, that's what it means to, in other words, you have to lift your pencil at the point if you're graphing it for whatever reason. A function is not differentiable at a point if the derivative doesn't exist at that point. In other words, if it doesn't have a derivative, no slope, unique slope at that point. So a function is not continuous at a break in the graph. A function is not differentiable at a break in a graph or where there's a sharp point in the graph. Now, what are some instances where you have sharp points or breaks in the graph, since that's where they're not differentiable? Well, a vertical asymptote is a break in the graph. So when you have a vertical asymptote, it's not differentiable there. A vertical tangent line, that we see one in one of the examples we're going to look at in a minute, but we're not going to elaborate on what that is at this point. You may or may not be acquainted with that in a later course. Can't say for sure. Or at endpoints on a graph. In other words, where you have a sharp point, there's no unique tangent line. You could have several that touch it at only one point, and the same thing at the end point of a graph. So it's not differentiable there. Let's draw a couple of conclusions here. Continuity does not imply differentiability. In other words, just because it's continuous does not mean it's differentiable. However, differentiable does imply continuity. So that might be important for us to answer some questions at the end. That seems like a little bit of gibberish back and forth. We just want you to think from kind of applying logic to it, where you have if-then statements and if A, then B, if not A, then not B, and that type of thing. We're just playing with you here to see if we can have you think a little bit. Let's look at example 1. Question: where is this function not continuous? At 1. Where is it not differentiable? Well, since it's not continuous at 1, it's not differentiable at 1, okay? And it's not differentiable at 2 because that's a sharp point. Now, we're not going to look over here at 3 here where it's you might say that's a sharp point. This is just a graph that we have lifted from another source for this particular exercise, and we're not going to, some people may argue whether that's an open, is it an open circle, is it a closed circle? We're just going to look at the points from here to here without considering the endpoints, realizing that it's never differentiable at an endpoint, okay? So let's go to the next page, if we can. Here we see example 2, same question. Where is this not continuous? It's not continuous at 1. Where is it not differentiable? Not differentiable at 1 because it's not continuous at 1, and not differentiable at 2 because it's a sharp point. Again, for the same reason, we're not going to discuss the endpoint here. Okay. Let's come down to example 3. By the way, this is just an aside. At 2 is this unique thing that you may or may not have heard before, and we'll leave it to some other time to discuss that. That's what I meant when I said that would be a vertical tangent line. It's a hairline difference between a vertical tangent line and a vertical asymptote, in that a vertical tangent line touches the graph just one time. It's a vertical line, but I want to leave it at that because that's not the thrust of this particular lesson. Example 3, where is this function not continuous? Well, obviously, it's not continuous at -1, and it's not continuous here at x equals 0. X equals -1 and x equals 0. So since it's not continuous, that means it's not differentiable at -1, and since it's not continuous at 0, that means it's not differentiable at 0. Okay, so here we have a few true-false questions just to talk about. The directions are, if it's false, show by way of an example, but this is not a live classroom situation. Otherwise, we would put a little angst to this part of the lesson, saying we might be called on, but you can relax. We're going to talk about this here as if, in other words, answered for you. If a function is continuous, it's differentiable, true or false? Well, think about it. What if it can be continuous with a sharp point, right? But it's not differentiable as a sharp point. So this is false. If it's continuous with a sharp point, it's not differentiable. If a function is differentiable, it's continuous. And differentiable basically means no sharp points and no breaks. So no breaks, it's continuous. So that's true. Not continuous implies not differentiable. That's true. If a graph is not continuous, you have to lift your pencil, then it's not differentiable. That's true. If it's not differentiable, it's not continuous for the same reason. If you have a V-shaped graph, it's continuous, but it's not differentiable at a sharp point. Perfect example would be the absolute value of x, which is a V-shaped graph. It's continuous, but it's not differentiable at the sharp point. If a mathematical statement states a function is differentiable, then it is understood that to be continuous, that's true. If a mathematical statement states the function is continuous, then it is understood to be differentiable, and that's not true. For the same reason, the absolute value function is continuous but not differentiable. And lastly, functions that are differentiable are usually easier to work with. The reason we mentioned that here, most of the time you'll see when you come to a mathematical rule or mathematical theorem, they'll start out by saying, first of all, f is a function which is continuous and differentiable. Of course, that's somewhat redundant because if it's differentiable, it's got to be continuous. So, but at any rate, that's how they usually word it. Functions, of course, people don't like to work with things that aren't functions because that means you get put in a number and you get the same two different answers. So it's not a function. They're not fun to work with. And graphs that have breaks on them, you've got to dance around the break. And functions that have sharp points and such, you've got to dance around the sharp points. So functions that are differentiable, that is no sharp points and no breaks in them, are much easier to work with. We just threw that in as a closing remark to make you think. Very short lesson, but it becomes very important, especially in the theory of calculus, which may come into play later. You need to understand, we're trying to give you the vocabulary that you need. And so please make sure you understand what we're saying here.